My name is Raphael Bousso, and I'm a professor here in the physics department. I work on quantum gravity, cosmology, and string theory. And I'm really excited that you're all here. Thanks for coming. And today what I want to tell you about is how physicists think, or more precisely, how theoretical physicists sometimes think when all goes well. And I want to start by making sure that you don't get the wrong idea. Physics is about trying to understand nature. And it's not about just making stuff up. And, well, so experiment is the final arbiter. You can have the most beautiful theory in the whole world. If it contradicts an experiment, it's dead. Now, in some sense, so far, all of our theories, all the theories that have ever been invented are dead, or at least pretty sick. And that doesn't mean that we haven't made any progress. And I'll try to explain in what sense that is true. It's true in a quantitative sense, that we are able to describe the world more and more accurately to a better and better approximation. And at the same time, also in a qualitative sense, we are able to describe more and more phenomena with less and less input in a more and more unified way. Now, sometimes progress is in fact led by experiment. You do an experiment and contradict some theory that you thought was right, and now you have to come up with either some modification or something radically new. But what I want to talk about today is a different way of doing physics, where you have two theories, each of which work really well, and neither of which has perhaps ever been contradicted by any experiment. And yet you know that either one or both of them is wrong, because they contradict each other. So, perhaps it'll be a long time until the experiment can be done, which shows which of these theories is wrong and how, but you already know there's a problem. And that's actually a great opportunity to make some progress. A wonderful example of that was the formulation of the special theory of relativity by Einstein, which happened in exactly this way. In the 1870s, electromagnetism, maybe 1860s, electromagnetism had been given its final form by Maxwell, a beautiful theory. And in that theory, the speed of light was just whatever it was. It was a fixed number. And for a few centuries already, people had understood Newtonian mechanics, where the speed of a train relative to you depends on how fast you're moving. If you're in another train, then the relative speed is much greater. Or if the train turns on its headlights, then and it's moving, then somebody at the train station should see light moving faster than the usual speed of light. Just as if somebody shoots a gun from the front of the train, the bullet will be moving faster than it would if you were standing still. That's Newtonian mechanics. That's how things work. Velocities just add. So it doesn't make any sense to say that the speed of light is always the same. It depends how you're moving, right? Yet electromagnetism said it's always the same. So what do you do? Well, you have to pick sides. Einstein went with electromagnetism and overthrew the Newtonian view of space-time in order to fit mechanics together with electromagnetism. Nice, and you can go for the radical option. Things just can't move faster than the speed of light. Velocities don't just add, and so on. So now he had special relativity. He still had a problem. There was a Newtonian theory of gravity that described extremely successfully how the planets move around the sun and how apples fall from trees. But that theory propagated information faster than the speed of light. If I take an apple and move it from here to there, the gravity of the apple instantaneously changes everywhere in the whole world. Not by very much if you're far away, but still, conceptually, it just is a complete contradiction. It can't happen. And so he had to put together special relativity with gravity. He also had to explain another problem to which I'll come back at the very end of this talk, why it is that all bodies fall at the same rate. That's something you can put in by hand into Newton's theory of gravity. But it's by no means required by the structure of the theory. And there are very similar theories like electrostatic attraction and repulsion, where this is not true. Not everything falls at the same rate in an electric field. Depends how it's charged. So you put these two things together, and again, Newton was the poor guy who was replaced, and he got his general theory of relativity. Today, it's the best theory of gravity we have. Still works. Gravity is no longer a force. It's bodies trying to fall as straight as they can in a curved space-time. That was the new idea. Now, you don't get to that resolution of the problem in one step. It took him 10 years. And that was Einstein. But first you have to know that there's a problem. Okay? And certainly people didn't know that there was a problem from experiments. Now, there were some experiments which, in hindsight, turned out to be anomalies that told people that Newton's theory of gravity was actually wrong. But Newton's theory of gravity is quantitatively extremely accurate, and almost all the motions of the planet have been successfully explained by it. Don't know what to do about this. Maybe I can turn on the volume. It's my cell phone. Thank you. Let's turn off the cell phone. That's easy. Try airplane mode. Okay. Thank you. Okay, let's go back up. Yeah. So this is what I wanted to say earlier. We say that Newton's been overthrown, but of course, for most purposes, works pretty well, right? So when we make progress, we might have a completely conceptually different way of describing the world, before and after Einstein. But your new theory had better reproduce all those successful predictions of the old one. And then, you find out that the planet Mercury, its orbit is off by 44 milliarcseconds, some ridiculously small angle in every century, off from the predictions you would get from Newton. And that's where it helps to have a completely new theory, in which gravity is no longer... No, but that's how you know that that's ultimately the right one, or at least the better one. And that's the sense in which experiment is the arbiter. Now, nobody's under any illusions that this is, again, just an approximation to something more general. Yet we've learned a lot. We've learned that space and time are dynamical objects. That they're not some fixed stage, which is completely fixed in the actors, the particles and radiation are just walking around in it. It's a stage that sort of bends as you walk on it, and sometimes collapses. And then we call that a black hole. Here's another example. So general relativity is one of the pillars of physics. I would say one of the two main pillars of fundamental physics. The other is quantum mechanics, discovered about the same time. This is a bit forced, but since we're on the subject of having clashes from which new theories emerge, you could say the picture that had come out of experiments about what atomic structure looks like, a hard nucleus, and then electrons that seem to be sort of orbiting around it. That picture clashed once again with electromagnetism, with Maxwell's theory, which told you that these electrons should radiate and spiral into the nucleus. The atom should not be stable. Again, a sort of catastrophic contradiction. But in this case, it was very important to have a lot of experimental data as well. Atomic spectra, the kind of the colors of the light emitted when you excite certain atoms, and they emit light. In this case, it was also many people, not just a sort of one towering figure like in the cases of Newton or Einstein. There was the work of many people put together that led to quantum mechanics, the theory of quantum mechanics. And quantum mechanics is this weird theory where you have this thing called the uncertainty principle. You cannot say at the same time that a particle is in a particular place and moving with a particular velocity. That's just not how nature behaves. A particle has a state, And that state may be such that the particle is definitely in a particular place, in which case it'll tell you nothing about its velocity. Or it may be the other way around, or it may be a sort of compromise between the two, where you know pretty well where it is and also pretty well how fast it's moving. But you don't know both arbitrarily sharp. That's really not such a big deal, because why should it be true at the microscopic scale for which quantum mechanics is important? Why should it be true that the intuitions that are useful for us based on how we developed in evolution and so on, why should these intuitions give us words for what we experience at the atomic or subnuclear scale? And so things can be things can be quite weird. The only thing that matters is if they're self-consistent. And what you care about is that, of course, you can predict the outcomes of experiments. And you can predict these spectral lines beautifully. You understand why the atom is stable and so on. So you're happy. So quantum mechanics is great. So now what's left? We've been doing really well unifying all the forces and so on. But there are these two things. Specifically, all of the other forces other than gravity, electromagnetism, the forces inside the atom, inside the nucleus of the atom, have been successfully explained through quantum mechanical theories by now. Quantum mechanics is sort of a general language, and then you have to figure out which exact set of words, describe the particles and forces we see. But that's been done. It's over. It's one of the most beautiful success stories in the history of humanity. It's the Standard Model. Unbelievably boring name for basically we know absolutely everything about how nature works, except for one thing. We don't know how general relativity can be fit into this quantum language. We don't know how to do that. When you try to do it, infinities blow up all over the place and you get nonsense. Okay. So what we've been looking for some time is a theory of quantum gravity. Theory which both takes into account that in quantum mechanics, for example, you can't talk about precise positions and velocities, whereas in general relativity you constantly do. But at the same time is able to reproduce general relativity in the limit where that theory works extremely well, which is at large distances. The reason that these two guys don't clash all the time in practical life is quantum mechanics is important at small distances. That's where the deviation from our classical intuition becomes large. Gravity is actually quite a weak force, but we feel it because it's only attractive, unlike electromagnetism, where you can have attraction and repulsion, and that cancels out for large bodies because they're typically neutral. But gravity, it builds up. It builds up. As you go to larger scales, there's more and more gravity because you're looking at more and more mass, because it's only attractive. And that's why gravity is important for large objects, for the universe as a whole in particular. It's a very important force. So most of the time, if you worry about the solar system of the universe, you don't need quantum mechanics. If you worry about an atomic nucleus, you don't need gravity. But what if we go to the Big Bang, for example? The universe is expanding, run it back in time, all the matter is sitting on top of each other about 13 billion years ago. You have a lot of mass, and it's in a very small space, or more precisely, it's at an extremely high density. And what are you going to do? Okay, so now you need both gravity and quantum mechanics. We can't do this experiment. Okay, it's too far outside of technological reach. Yeah, we can't create these kind of densities in the lab. But we know that there are regimes in nature where you have to know quantum gravity to give an answer. So what do we do? How do we make progress on this problem? Well, it's very hard to do it in one step, it seems, because we've tried for some time. So you need to find ways of sharpening the conflict. You need to find some sort of a bar with which you can pry the door open a little bit. Now, as I already said, for the Big Bang, or if the universe recollapses, a big crunch, where you have a lot of matter in a very small amount of space, quantum gravity would certainly be important. We would need it in order to make any kind of prediction about what happens there. But it's unclear how to even approximately solve this problem, how to begin to describe this regime with what we know, by putting together what we know. And the rest of this talk is really devoted to explaining to you how black holes have become an unbelievably valuable and exciting tool for prying open the door, for catching a glimpse of some of the properties that a quantum gravity theory must have. So that, it just nails down a few points. And maybe from there we can start interpolating or extrapolating or whatever we need to do and starting to put together a theory, the way that Einstein started with a few principles, and then from that constructed a new theory. So that would be the hope. And I'll give you, for the most part, I will be talking about a success story coming from black holes where they taught us something new. We learned the lesson. I think we've incorporated it. It's really valuable. It gives us a useful data point for how to construct quantum gravity or two. But I want to end with a wide open question that black holes allow us to pose and which we have not yet answered decisively. And it's actually, the fact that this question is still open is sort of news. It's less than a year ago that we realized that we didn't in fact understand this question correctly. So in that sense, this talk is actually fairly up to date. And I'm talking about something that to me is actually an incredibly exciting development, maybe the most dramatic in my career. But let's first start with a more established story. So first of all, let me just tell you what black holes are. Black holes are regions from which nothing, not even light, can escape. So think about, there's lots of analogs people have. One that I like is quicksand. Think about a sort of pool of quicksand. And the sand is kind of sucking people in. And if you're, farther out from the center of the pool, then the sand is moving pretty slowly. And at the center, it's moving really fast. And so, if you step in just a little bit and then you run out at top speed, you can still make it out because you're outrunning the sand pulling you in. Okay, but there comes a certain place where, if you've moved in this far, run as fast as you want, the sand is pulling you in faster. Okay, the space is sort of contracting underneath you, and it's doing it faster than you can counter it. Or it's like running on a treadmill that's running faster than you can run. You move backwards in the end. And the top speed here, of course, is not yours, but the speed of light. That's what's relevant. And if you cross this, so this is sort of like a line of no return. The reason I like this analogy is that when you just look locally at this line of no return, there's just some sand moving there. There's actually nothing special. It doesn't look that different from, where the sand is moving a little bit more slowly on one side and a little bit faster on the other. And the black hole horizon is kind of like that. There's no signpost saying, here's the black hole horizon. It's just like, you shouldn't have gone that far. Now, how do black holes form? They form if you put too much stuff in a too little space. Now, it's actually hard for us to do this, but it happens out there in the universe. So you could try doing this by compressing matter, and to a theoretical physicist, it's important that, in principle, you could make a black hole essentially of any size, very small, extremely large. By doing this, the density of matter, by the way, doesn't have to be as large when you make a big black hole, but you need more mass. How does it actually happen for the black holes that we think we've seen? Those form by gravitational collapse, for example, when a star runs out of fuel and collapses in on itself under its own gravity. And then once a black hole is formed, it can gobble up more matter, things that come its way, and grow further by accretion. If you throw something into a black hole, it gets bigger. It means the sphere of no return moves out a little bit. That sphere is called the horizon. Okay, so astronomers have found evidence for at least three, but let's say two types of black holes. One class are so-called stellar mass black holes. That's just fancy language for a star collapsed and formed one of these. And the other are supermassive black holes. It appears that most galaxies have one at their center. The Milky Way does. And these guys are millions to billion times heavier and bigger than the solar mass black holes. And they eat other stars. That's what they do. Okay. And really, I don't care about any of these black holes at all. I just care about the fact that black holes exist. And it helps to know that, they're not just predicted by general relativity, but they are, in fact, seen by astronomers in the best sense that one can ascribe that word to something that doesn't have anything come out of it, including light. But what you see is that things orbit an incredibly compact object that there's just no other physics known that could make that object so massive and yet so small. All right, so we know from general relativity what a black hole looks like, and here is a cartoon. In various ways, almost everything about this cartoon is wrong. For example, I've already told you this, the horizon is not a special place. So if you cross this line of, or in this case, sphere of no return, space doesn't suddenly become blue, it's still black. But we had to show somehow where the horizon is. So the other thing that's wrong is that the singularity is somehow spatially in the center of the black hole. Like you could go there, find a place where space and time are really tightly curled up and densities become high, and then maybe move away from it again because you think it's dangerous. No, the singularity is an end of time. Because you can't help moving forward in time, you can't help hitting it and dying if you fall into the black hole. There are probably some other problems with this picture, but those are the main ones. But still, you get the basic idea. There's some exterior. If you don't cross this event horizon, then, given enough of an effort, you can make it out and not fall into the black hole. If you do cross it, you end up at the singularity. Let's see, have I said everything? Yeah, so you can be static on the outside of the black hole. You could, for example, hover and have nothing change. But once you're inside, you can't change the fact that space is collapsing underneath you. It's automatically a dynamical space-time. Okay. Now, one thing that you might ask is, what happened to the star that formed this black hole? Where is the matter? Shouldn't that be sitting here at the singularity somewhere? Maybe packed closely around it. But wait, we already know the singularity is not a place in space. It's an end of time. And it turns out that, well, of course, if you collapse with the star, you got, I don't know, a protective suit on, and you're sitting on the surface or somewhere inside the star while the star is collapsing, then yes, you're inside the black hole and you do see the star. And then you and the star get compressed to infinite density. But if you wait a little while after some black hole formed far away, and then you look at the black hole, or you jump in, it doesn't matter. The black hole always looks the same. You don't see any trace of the matter anymore that made that black hole. This is an incredibly important point. I mean, it's easy to say, but it's important to appreciate it. This is not usually true when we compactify something, I don't know, in the garbage compactor, and we push it away. We can always go back and look, and we can figure out what it is that was in this garbage and so on. But for a black hole, it is mathematically impossible, according to general relativity, to tell what formed it, other than what mass it had, the total mass. That's all the information you're going to get, and angular momentum, charge, but really almost no information. I mean, it could have been just banana peels, it could have been just apple trunks. All that you know is the mass. And again, it doesn't matter if you stay outside or if you decide to fall in and look for the matter there. If you've waited long enough after the black hole formed, well, for some reason, general relativists call this the no-hair theorem. The black hole doesn't have any hair. I have no idea what this has to do with hair. It's a universality. Okay, the black hole is described by only 3 numbers: mass, charge, and angular momentum. That's it. I guess I already said that. Okay, so why is this such a big deal? Why is this a problem? It's a problem because this means the black hole can violate the second law of thermodynamics. I'll try this again. The black hole can violate the second law of thermodynamics. You're supposed to be outraged. Okay, yes, thank you. Thank you. Say it ain't so. Exactly. This is absolutely terrible. This is basically the one thing that it's just a non-starter. If you have any theory, just it's there's, I don't know who is that, Eddington or somebody, if it conflicts with experiments, the experiments are probably wrong. But if it conflicts with the second law of thermodynamics, forget it. So here's why this is such a problem. Okay. So I have to tell you what the second law is and what it actually says, and then you'll see why black holes are a problem. The second law is the statement that the entropy of a system cannot decrease. Actually, it's extremely unlikely to decrease. Okay, by extremely, I really mean extremely, extremely, extremely. And so that doesn't help much because I haven't told you what entropy is. And this is the point in the popular lectures where people usually talk about entropy as disorder, and you know how your child's room, you leave it alone for a while and the disorder always increases. And I don't know. So let me try to make this a little bit more precise. And if this fails, then just think of a children's room. Okay, so I could have done this with toys. There's not so many ways to arrange toys on a shelf, but there's really many different ways you can arrange toys in a messy pile. You just call it a messy pile, but if you think about how many different ways you could make a messy pile, it's huge. Right? So what entropy does is it measures the number of different microscopic states, and I'll tell you what I mean by that, of some system that we would describe as, let's say, a crystal of this and that size. Okay, some system that we describe with 2 or 3 words, some macroscopic system. How many different ways could you actually make this thing? Okay. And of course, even though this may not be how you usually communicate with other people, but by making messy piles in different ways and having some translation between messy pile made one way means I like the eggs this morning, messy pile made the other way means I would like to go to sleep earlier. You could actually communicate information with messy piles. You can communicate much more information with messy piles than with toys arranged cleanly in a shelf. Or let's go to something more reputable like crystals. So a crystal at 0 temperature is sort of an idealized version of a nicely arranged shelf. It has only one possible state. Well, if I tell you it's a silicon crystal and it's, I don't know, an inch cubed. Okay? So then that's it. There's no more than one way of making such a crystal, because basically once I've told you where one corner is, the location of all the other atoms is completely fixed by the spacing in the crystal atoms. There's nothing else. I mean, of course, I'm idealizing here a crystal without impurities and so on, but I hope I get to do that. I'm a theoretical physicist. So there's, but I said it's 0 temperature. This is very important. This has to be at absolute 0 temperature and isolated from the rest of the world. And then there's only one way to make a crystal. All right, but now let's put it back at room temperature. And now what happens is that all the atoms will wiggle a little bit. Having more temperature basically means that to each fundamental constituent of the object, you're giving a little bit more energy. The energy distributes itself pretty evenly among all the atoms. Higher temperature, there's more energy per atom. Lower temperature, there's less. But there is some energy that each atom gets to use to do stuff with, like wiggle around. And that's actually what we perceive as warm. When you touch something warm, the atoms are wiggling more. Okay. Now the thing is that atoms can wiggle in lots of different ways. In fact, classically, they could wiggle in infinitely many ways, but thanks to quantum mechanics, each atom can only wiggle in a few different ways. But the more energy I give it, the more ways it can wiggle in. Okay. And so if you have a lot of atoms, you basically have a lot of different ways that this crystal can wiggle. Of course, you don't see this wiggling because it's happening on an atomic scale. Not perceptible to us other than the average effect of the warmth of the crystal. Okay. Now, what is entropy? Entropy is basically the number of different ways that the atoms could be arranged at a given moment inside the crystal, wiggling included. And more precisely, it's the logarithm of that number. So a better way of saying that is it's how many digits you need to write that number down. Okay. And in fact, that's in fact a much easier thing also to compute, because let's say that each atom can wiggle in 10 different ways. Okay, and you've got, well, typically something like 10 to the 22 atoms, some number of atoms in a piece of crystal. Well, that's how many digits you're going to need to write down what each atom is. For the first atom, I have to write down a digit from 0 to 9. For the second one, I have to write down a digit from 0 to 9. And once I've written down all those digits, 10 to the 22 digits, so the number of digits is a 1 with 22 zeros. It's huge, right? That the number of states that a crystal can be in at room temperature, a little crystal like this, is gigantic. But it's roughly, the entropy is roughly the number of atoms. Okay, it's a big number. Okay, now, of course, in practice, we have no idea what each of these atoms is doing. Okay. And so one way of thinking about this is that entropy is a measure of our ignorance. If all I know is that I have a crystal at room temperature, well, then 10 to the 22 is basically a measure of how much I don't know. Right? No, that's really... Now, if, on the other hand, I could select a particular state of wiggling by some super advanced technology that I've invented, which I could actually do for incredibly tiny crystals, by the way. But the 10 to the 22 atoms is just hopeless. If I could prepare the crystal in a particular state, then once again I could use the crystal to send you a message. You know, we both have the same dictionary. This state means that. This state means that. So I can send, in fact, 10 to the 20, well, exponential of 10 to the 22 different messages. Some incredibly large number of messages I can send. And in that sense, while it's true that, you know, in most cases, 10 to the 22 is telling me how much I don't know about the crystal, it also tells me how much information the crystal has or could have if I was able to control it. It's a capacity for information. Okay, so that's it for entropy. That's what entropy is. It's a capacity for information or a measure of our ignorance if we don't have that information. And now, back to the second law. I said the entropy of macroscopic systems is extremely unlikely to decrease with time. Macroscopic means like the stuff we deal with in everyday life. If I delete that word, then I also have to delete extremely. Now, this is true almost by definition. Once you understand that entropy is just a way of counting how many different states there can be. For example, one should really turn the logic around. Like when you're throwing an ice cube into a glass of water and you let it sit there, what's the ice cube going to do? It's going to melt. The water is going to get a little bit colder, the ice is going to get warmer. Now, in fact, it does not conflict with the laws of physics in principle for the ice cube to get colder and the water to give it some of its energy the water to extract some energy from the ice cube and get warmer. But it never happens. Why does it never happen? Why does the ice always melt? Why does the ice always give energy to the water and the water never gives any, why does the ice always take energy away from the water and get warmer? And why does it never happen the other way around? Well, you can calculate. I'm not going to do that. But you can calculate how many different ways the atoms can wiggle if the ice got colder and the water got warmer. And you can compare that to how many different ways the atoms can wiggle if it goes the normal way and the ice warms up and melts. And it turns out that the second number is insanely, immeasurably larger than the first. I mean, so incredibly larger that the probability that you're in one of those rare states where the ice gets even colder, it's just completely negligible. You can do this experiment for the whole age of the universe. It's not even once going to happen. And that's why things equilibrate. Most of the states have the energy divided evenly among all the particles. And very few states like to give more energy to one system at the expense of another. All right. So I'm sorry, I already said this. So this is how the second law operates. It's basically just a statement about statistics. It's just saying you're probably in one of those states that are far more numerous than in one of those states that are incredibly rare. That's all there is to it. It's not like there's a law against energy flowing from the water to the ice. It could happen, it's just super unlikely. Okay, but then again, we know how to take water, put it in the freezer, and turn it into ice. How did that happen? More generally, if I take my warm crystal and put it in the fridge, its entropy goes down. The atoms in the crystal have fewer different ways of wiggling now because the temperature of the crystal goes down. So let's put the crystal in the fridge. The entropy of the crystal decreases. Doesn't that violate the second law of thermodynamics that was supposed to be so sacred? And the answer is no, it doesn't. But it's important to take into account that this fridge really has to radiate heat. It's doing this here at the back. And it's heating up the atmosphere outside the fridge. It's heating up the room. And when you look at the combined entropy of the air in the room and the crystal, that is going up. Again, that's a calculation you can check. That is going up, and it had to go up because the second law, again, it's just a statement about statistics. The fridge wouldn't work if it didn't go up, if it relied on some incredibly unlikely piece of luck. Okay. And so now, the fridge is really the important analogy here. Because a black hole appears to be like a fridge that doesn't heat up the air in the room. It's a fridge that you can put the crystal in, destroy the entropy of the crystal, and pay no price. Create no compensating entropy anywhere else. Right? Well, because the crystal has gigantic entropy 10 to the 22. The black hole, after you've thrown the crystal in, is still just described by these three numbers. It doesn't have a lot of different options of what it can do. It has a mass, a charge, and an angular momentum, not a lot of different combinations. That's the problem. That's the problem with black holes. That's why this no-hair theorem is so troublesome. Now, what could we do to rescue the second law? What could we do to repair this situation? I have to do something here to one at a time. Okay. What can we do to repair the situation? Well, first we need some hints. We need some hints. Some slightly weird things that need to be put into the right place. And here was a slightly weird thing. In 1971, so more than 40 years ago, Stephen Hawking, who was my PhD advisor, proved that the area of a black hole horizon cannot decrease. He wasn't my PhD advisor then, of course. The area of a black hole cannot decrease. So no matter, now this sounds obvious because, of course, when you throw something into a black hole, the black hole gets bigger, so the area of the horizon grows. So the black hole can't spit anything out because it's a black hole, so the other direction doesn't happen. It's actually not so trivial to prove this for rotating black holes and so on. So it was quite an accomplishment. But what was amazing about this is that there aren't a whole lot of laws in physics that are inequalities like that are some quantity can only ever increase or remain constant but never decrease. And of course, it sort of comes to your mind that this is something that we've been saying about entropy for some time. Right? That's kind of like what entropy is. So the area of this sphere of no return is behaving in the same way as what we're used to from entropy. There were a couple of other hints that the laws of thermodynamics had sort of mirror images in the laws of how black holes behave. This was not the only one. Okay. And at the same time, Bekenstein was really bothered by this possibility that you could destroy entropy by violate the second law by throwing stuff into a black hole. So he put 2 and 2 together. Okay, we don't want to destroy entropy. The horizon of a black hole mathematically behaves already exactly like entropy. Why don't we just say that it is entropy? Okay, why don't we just say that it is entropy? The entropy of a black hole is given. This is one of the most beautiful papers I've ever read. Maybe not the most beautiful ever written, but because it's so simple, right? This is how you want things to work. It's almost never, of course, going to happen, but in hindsight, it seems so simple, but you have to know which questions to ask. The entropy of a black hole is just its area measured in certain units called Planck units that I'll come back to. And the idea is simple. If you throw the crystal into the black hole gets bigger. So even though you've lost the entropy of the crystal, you now have some analog of the air in the room. The black hole area has gotten bigger, and that's the thing that compensates. Okay, so that's called that is the second law. Wittgenstein invented a new name for it, the generalized second law, which basically says that the total black hole entropy plus all matter entropy in the universe does not ever decrease. Okay. So again, if you throw the crystal into the black hole, yes, you do destroy the entropy of the crystal, just as when you put the crystal into a fridge, you lose some entropy of the crystal. But something else makes up for it. Black hole grows. Its entropy, according to Wittgenstein's new formula, where entropy equals area of the horizon, increases. That compensates. Total entropy might now actually increase. We don't have an obvious contradiction. But this is a good example of how, trying to resolve a very concrete conflict, as opposed to just saying quantum mechanics and gravity don't fit together, I don't know what to do. Resolving a very concrete problem leads to progress on a much deeper and broader problem. Okay, one question that is raised by Wittgenstein's conjecture is, well, fine, okay, a black hole you say has entropy, but what are the atoms that are doing the wiggling? Where did you get that from? I mean, you can't just say a black hole has entropy. Something has to do the wiggling. Something has to correspond to all these different states that the black hole can be in. And general relativity says there aren't a lot. Mass charge, angular momentum, that's all I get to say about it. That's one question. The other question is the entropy of the black hole actually enough? Does the black hole area increase by enough to compensate for the lost entropy of the crystal? I mean, after all that we've shown so far is that there's no longer an obvious problem, but whether it works out in terms of, the numbers, different question. So let's first discuss the first question, what wiggles? And for the largest part, we still have absolutely no idea. Okay. But we know it has to do with quantum gravity. Roughly speaking, because that's the only thing it can be, there's only one way that you can measure area in terms of fundamental constants. And you need both Newton's constant of gravitation and Planck's constant, that is fundamental to quantum mechanics, to piece something together that gives you a length or an area. Some unit in which you can measure, some not completely arbitrary unit, in which you can measure the horizon of the black hole, called the Planck length. So you have, in Wittgenstein's formula, you have both quantum mechanics and gravity already in that very expression. So that expression, if it comes from some more fundamental theory, if we understand what this entropy is counting, it must be counting some objects that live in a quantum theory of gravity. Okay. And so we still don't know what that quantum theory of gravity is, just because he said this, but we know one thing about it. It has to give me that many states for a black hole. And that has turned out to be an incredibly difficult thing to reproduce. And to the extent that it has been done, which is only for very special classes of black holes, that's basically the claim to fame of string theory. Okay, it was able to explain these states in terms of things called deep brains and so on. But not for all black holes, just for very special ones, not like the ones we see in the universe. So a lot of work to do. The other thing that's, so this is what I just said. So this is one of the major unsolved problems in physics. Understanding what the nature of these states is and reproducing Bekenstein's formula from a more fundamental viewpoint. Your theory better agree with that number, entropy equals area. Okay. The other question that I raised is it enough? Will the black hole increase in area by enough to compensate whatever matter entropy I lost? And that's another amazing subject to some extent. I'll get there. But I've given you an example here. That's just one example. Okay, so we'll just try it. Okay, let's say a star collapses. To start with, the star has entropy 10 to the 57. That's roughly the number of atoms in the star. Okay, that's how many protons are in a star, not atoms. So the star collapses because it ran out of fuel, and for certain stars that have enough mass and so on, it will form a black hole. Now it will also shed some of its mass, and so this is an oversimplification, but it gets the point across. What you have at the end, a star like a sun is 700,000 kilometers in radius. At the end, you have something that's a few kilometers in radius. It's amazing how much denser a black hole is than a star. The same mass, just a few kilometers in radius. So the horizon area is a few square kilometers. We're supposed to measure this in units of the Planck area. A Planck length is 10 to the minus 33 centimeters about. So it's like, I don't know, it's to the size of a nucleus what the nucleus is to an orange, or if I remember correctly. I mean, it's really small. Okay, it's very, very small. You're measuring kilometers by putting little Planck tiles on these square kilometers. How many tiles? 10 to the 77 tiles will fit. Okay, so that's your new entropy after all is said and done. So it looks like the entropy did go up by a factor of 10 to the 20. It went up a lot. Okay, so the generalized second law is working just beautifully for stars collapsing into black holes with a lot of room to spare. Okay, now you can keep going like this and come up with other examples. And you soon realize that it always works. You don't quite understand why it always works. Why can't we find matter that has so much entropy, but not that much mass, so that when I turn it into a black hole, the entropy actually goes down? Because what sets the entropy of the final thing, the black hole, is how much mass I had, but what sets the entropy of the initial thing is how much entropy I had in the matter system that I collapsed. But you try this over and over and over, and you just cannot invent any matter systems that violate the generalized second law. Unless you invent really crazy stuff we've never seen, like matter with negative energy and so on. So with realistic matter, you can't apparently do this, so it's time to turn the logic around. Let's take the generalized second law as a fundamental statement and try to conclude something from it. Well, let's say this room was a sphere for simplicity, okay? I can tell you something about this room without knowing anything about what's in it, okay? Namely, I'm going to measure the area of the walls, and I know that I could always convert this room into a black hole of the same area by just crashing more mass into here, okay? And so I know that I can get to a final state in which I know exactly what the entropy is, the area of this room measured in Planck units, okay? That means that whatever there was in this room now had to have less entropy than that. But now let's forget about crashing mass and so on. That just means whatever is in this room now has to have entropy less than the walls of the room measured in Planck units. Just because I could have made a black hole out of it. That's amazing. Right? I didn't have to know what the fundamental constituents are. Are they molecules, atoms, quarks, strings? I just have to know how big the room is, and I have a statement about how much information there could possibly be in it. That's one thing that's stunning. And the other thing that's stunning, so I have a universal limit on the amount of information that can be stored in region space. Universal meaning I don't have to know what the stuff is that is in here. Okay? But the other thing that's stunning is that it makes the world look like a hologram. The thing that's stunning is that it goes like the area. It has nothing to do with the volume of the room. If I double the radius of the room, you would think that the maximum amount of information would somehow be like, 8 times as big, because I've made the volume 8 times as big. So it's like the cube of the radius. But no, the maximum information only becomes 4 times as big because the area of the walls only go up by a factor of 4. That should be really shocking to us because it conflicts with what physicists call locality and what ordinary people would call my ability to scratch my head over here while my friend is scratching his head over there without that interfering with each other. So this is actually very surprising. So we've learned 2 amazing things from this line of reasoning. We've learned that the maximum information does not depend on what the fundamental constituents of nature are, but is related to the area of surfaces in space-time. And secondly, that in fact quantum gravity is somehow non-local. So I can't. Yeah. So I should explain this better. If I could do independently different things in every. Let's divide the room up into little cubes, maybe of the Planck size. If I could do something independently in every cube, then clearly the amount of information I could store in the room would go like the volume. Each cube basically would contain maybe 1 bit of information or a few bits. That doesn't really matter. The point is that it would grow like the volume. If I have more volume, well, that's how many more cubes I can fit in. But that doesn't happen. Why can't I do this? Well, what happens is that if I tried to do this, the room would actually collapse into a black hole. But we don't really understand that in detail. We just understand it by doing lots and lots of examples. It turns out that with realistic matter, encoding information always costs energy. And it costs enough energy to prevent me from doing what I just described. So energy, of course, what we're holding fixed is the size of the room. So I can only have so much energy before it collapses into a black hole. There's a maximum mass I can have. And that means I can only store so much information. Now, by doing examples like, over and over again with different tricky ways of storing information in computer chips, in fluctuations of fields or whatever, you would, of course, never discover that it goes like the area. You would just discover that somehow you can't make it grow like the volume. So you really needed this independent argument to have that insight that somehow areas of surfaces, for a fundamental reason, the second law of thermodynamics, have something to do with information. And it turns out that even though I've tacitly assumed that this room is not already inside a black hole, rapidly collapsing and so on, you might think that this is actually not a very general statement. It turns out that there's a completely universal statement that you could not have derived from how black holes in the second law of thermodynamics behave. That applies to the universe as a whole, that applies deep inside black holes, that always connects entropy with information. It's a completely universal law, which I found. Now, it's a universal law. Apparently, nobody's found a counterexample, but we don't know where it comes from. It's more like a conspiracy or a coincidence at this point. And it's not something that we really understand from a deeper point of view. What can explain this? Again, there's gravity in this law and there's quantum mechanics in this law. To really understand this, we need a quantum theory of gravity. What have we learned? Well, one more data point about quantum gravity. The way that space-time, this classical object that Einstein described, and it can be curved and it explains gravity, the way that comes out of this quantum theory of gravity, whatever it is, had better have it built in that you can never have more information than an area's worth in any given region of space. It had better have these coincidental, conspiratorial relations that we now see come out as, it couldn't be any other way. So that's how it helps. Okay, so I need to start finishing, which I think we're on track. So this is what the holographic principle, what that expression means. It's basically just a statement of elevating this conspiracy to a fundamental principle that should be explained by some deeper theory. I wanted to close, as I promised, on a story that hasn't yet wrapped up so nicely as the story of this generalized second law and of information and the holographic principle. Um, there is still a crisis that comes from black holes, which is unresolved. We thought it was resolved, but turns out a year ago we figured out it's not. Or more precisely, some horrible people in Santa Barbara spoiled everything and figured this out. But you know, it's really been the most beautiful thing that's come my way in a long, long time. How did this problem start? Well, back to the 70s, early 70s, this is what Bekenstein looks like now, but he was actually like a 22-year-old grad student when he did this amazing work. And nobody believed him, not just because he was so young, but because his proposal that black holes have entropy, that they have a capacity for information, simply didn't make any sense. Why? Because the laws of thermodynamics tell you that if something has energy and it has entropy, then it must have a temperature. It must. It's the first law of thermodynamics. Can't be any other way. Something that has a temperature emits heat. It emits radiation. And we all know that a black hole cannot emit anything. And in fact, one of the sharpest critics was Stephen Hawking, until he did some calculation that he did really for a different reason. And he did it for rotating black holes from which one can, in fact, extract energy, and there's nothing really terribly mysterious about it. But he discovered that the black holes keep emitting stuff even if they're not rotating. That was strange. Black holes, in fact, do emit radiation. That's what he found. Okay. Now, I don't have any way of describing this calculation, but it has quantum mechanics in it. Not quantum gravity, really, but just it treated the matter in a quantum mechanical way, but the black hole was just the usual black hole from Einstein's gravity theory. But by putting it together in the right way, we found that black holes actually are able to produce particles that come out of the black hole. Quantum mechanics, in a way, gets to violate a tiny little bit the rule that black holes can't emit everything. That rule, Hawking's own area theorem, was only proven for the strictly classical theory. Okay. And so the black hole, well, this radiation is energy. It is mass by E equals mc squared. Something that has to come from somewhere, it comes from the black hole. The black hole gets smaller as it emits radiation and eventually fizzles away completely. For astrophysical black holes, this effect is far too weak to be of any relevance. But again, I'm a theorist, so I care about the fact that it's there and what are its consequences. Well, this was a triumph for a lot of people. I mean, Hawking, of course, but also Bekenstein was pretty happy. He was vindicated. You know, he had stuck his head out and said something completely crazy that turned out to fit in exactly with the calculation that Hawking did, which was a completely different calculation. Okay, so black holes are like other objects. They can store information, and they can return it when they evaporate, except that they don't. Okay, so this is great. So now you have this crystal that you're handing over to your friend. It's got some message stored in precisely how the atoms wiggle, and your friend can read it off, except that while you're handing it over, the crystal completely randomly switches to a different state, so that the message that your friend reads off and what you put in are utterly unrelated to each other. Another way of, so this is a clash, okay? It's a beautiful crisis because it forces us to choose, as it turns out, between the central principle of quantum mechanics and of gravity. It's a fantastic opportunity of progress. So I'll just say one more thing about this. The reason that it's so terrible that the information that is in this cloud of Hawking radiation has nothing to do with how I made the black hole is that I've just violated a central principle of quantum mechanics, which we call unitarity and which you might call the conservation of information. It's just a statement that if I know the quantum state at one time, the state of the system, I can predict it at a later time, I can retrodict it or reconstruct what it was at an earlier time. Information is never lost in quantum mechanics. It's very difficult to even write down a quantum mechanical theory in which information is lost. That's one principle that appears to be violated by black holes. Well, if you do Hawking's calculation, whose starting point is this famous equivalence principle from which Einstein derived the general theory of relativity. Basically, that if you're in free fall in an elevator shaft, it's like being in outer space. It's like you can't distinguish those situations. It just means you don't feel any gravity. Either way. Okay. That's the starting point of Hawking's calculation, and that's what leads him to decide that quantum mechanics, or a central principle of quantum mechanics, is breaking down. But of course, you can turn the tables on it, and pretty much the tables have turned. Today, very few people will believe that information is really lost. But what we've learned is that really means, we can't have it both ways. If information is not lost, that means that the starting point of Hawking's calculation has to be wrong, and the equivalence principle goes out the window. So it really forces us to choose between what's at the core of the two theories that we've been trying to put together. That's great. That's great. We're pushed towards a really sharp conflict, and hopefully at the end of that we will have learned something. Thank you. My name is Raphael Bousso, and I'm a professor here in the physics department. I work on quantum gravity, cosmology, and string theory. And I'm really excited that you're all here. Thanks for coming. And today what I want to tell you about is how physicists think, or more precisely, how theoretical physicists sometimes think, when all goes well. And I want to start by making sure that you don't get the wrong idea. Physics is about trying to understand nature. And it's not about just making stuff up. And so experiment is the final arbiter. You can have the most beautiful theory in the whole world. If it contradicts an experiment, it's dead. Now, in some sense, so far, all of our theories, all the theories that have ever been invented are dead, or at least pretty thick. And that doesn't mean that we haven't made any progress. And I'll try to explain in what sense that is true. It's true in a quantitative sense, that we are able to describe the world more and more accurately to a better and better approximation. And for a few centuries already, people had understood Newtonian mechanics, where the speed of a train relative to you depends on how fast you're moving. If you're in another train, then the relative speed is much greater. Or if the train turns on its headlights, then and it's moving, then somebody at the train station should see light moving faster than the usual speed of light. Just as if somebody shoots a gun from the front of the train, the bullet will be moving faster than it would if you were standing still. That's Newtonian mechanics. That's how things work. Velocities just add. So it doesn't make any sense to say that the speed of light is always the same. It depends how you're moving, right? Yet electromagnetism said it's always the same. So what do you do? Well, you have to pick sides. Einstein went with electromagnetism and overthrew the Newtonian view of space-time in order to fit mechanics together with electromagnetism. Nice, and you can go for the radical option. Things just can't move faster than the speed of light. Velocities don't just add, and so on. So now he had special relativity. He still had a problem. There was a Newtonian theory of gravity that described extremely successfully how the planets move around the sun, and how apples fall from trees. But that theory propagated information faster than the speed of light. If I take an apple and move it from here to there, the gravity. But Newton's theory of gravity is quantitatively extremely accurate, and almost all the motions of the planet had been successfully explained by it. Don't know what to do about this. Maybe I can turn on the volume. It's my cell phone. Thank you. Let's turn off the cell phone. That's easy. try airplane mode. Thank you. Okay, back up. Yeah. So this is what I wanted to say earlier. We say that Newton's been overthrown, but of course, for most purposes, works pretty well, right? So when we make progress, we might have a completely conceptually different way of describing the world, before and after Einstein. But your new theory had better reproduce all those successful predictions of the old one. And then, you find out that the planet Mercury, its orbit is off by 44 milliarcseconds, some ridiculously small angle in every century, off from the predictions you would get from Newton. And that's where it helps to have a completely new theory, in which gravity is no longer... No, but that's how you know that that's ultimately the right one, or at least the better one. And that's the sense in which experiment is the arbiter. Now, nobody's under any illusions that this is, again, just an approximation to something more general. Yet we've learned a lot. We've learned that space and time are dynamical objects. That they're not some fixed stage, which is completely fixed in the actor as a particle formation, and at the same time also in a qualitative sense, we are able to describe more and more phenomena with less and less input in a more and more unified way. Now, sometimes progress is in fact led by experiment. You do an experiment and contradict some theory that you thought was right, and now you have to come up with either some modification or something radically new. But what I want to talk about today is a different way of doing physics, where you have two theories, each of which work really well, and neither of which has perhaps ever been contradicted by any experiment. And yet you know that either one or both of them is wrong, because they contradict each other. So, perhaps it'll be a long time until the experiment can be done, which shows which of these theories is wrong and how, but you already know there's a problem. And that's actually a great opportunity to make some progress. A wonderful example of that was the formulation of the special theory of relativity by Einstein, which happened in exactly this way. In the 1870s, electromagnetism, maybe 1860s, electromagnetism had been given its final form by Maxwell, a beautiful theory. And in that theory, the speed of light was just whatever it was. It was a fixed number. If the apple instantaneously changes everywhere in the whole world. Not by very much if you're far away, but still, conceptually, it just is a complete contradiction. It can't happen. And so you have to put together special relativity with gravity. You also have to explain another problem to which I'll come back at the very end of this talk, why it is that all bodies fall at the same rate. That's something you can put in by hand into Newton's theory of gravity. But it's by no means required by the structure of the theory. And there are very similar theories like electrostatic attraction and repulsion, where this is not true. Not everything falls at the same rate in an electric field. It depends how it's charged. So you put these two things together, and again, Newton was the poor guy who was replaced, and he got his general theory of relativity. Today, it's the best theory of gravity we have. Still works. Gravity is no longer a force. It's bodies trying to fall as straight as they can in a curved space-time. That was the new idea. Now, you don't get to that resolution of the problem in one step. It took him 10 years. And that was Einstein. But first you have to know that there's a problem. Okay, and certainly people didn't know that there was a problem from experiments. Now there were some experiments which, in hindsight, turned out to be anomalies that told people that Newton's theory of gravity was actually wrong.